This is Ms. Page, and this lesson is going to involve a type of problem that often ends up with the setup being a rational equation, which is what we've been studying. And we have classified this as a proportional reasoning problem, where we're looking at situations in which we have ratios, and those ratios are going to change by a certain amount, and then we want to figure out what that amount would be. So for example, here it says Carol made 24 sugar cookies and 18 chocolate chip cookies. If she wants 60% of the cookies to be chocolate chip, how many more chocolate chip cookies would she have to make? So if we figured out the ratio of chocolate chip to all the cookies, it would not be 60% in this case. So we're looking to see how many more chocolate chip would be necessary to raise it to the 60%. So we let our variable be those extra chocolate chip cookies. And we're writing a ratio, a proportion, that gives us the number of chocolate chip that we would have, which is our 18 that we already currently have, plus the extras that would be made. And then the total number of cookies would be, actually, remember, our 24 sugar plus our 18, that's this 42 right here, and then plus the extra cookies that are being made, the extra chocolate chip cookies. This ratio, which is the new cookie amounts, is what we want to be a 60% ratio, 60% chocolate chip to the total number of cookies. And that creates this equation right here, which is a rational equation because we have a variable here in the denominator. So we're going to do problems similar to this today. All right, so here is our first example. So in this particular problem, there are 120 men, and there are 160 women who are registered to attend a conference. So assuming that no more women register for the conference, the question is how many more men would need to register to make the percentage of men 55%. So right now the percentage of men would not be 55% of the total number of people. As we have to remember, it's not men to women, it's men to everybody. So our ratio, what we're looking at, is men to the total number of people. So right now that would be 120, and then our 120 plus our 160, which would be 280. We want to change the number of men so that this ratio will become 55%. So I'm going to define my variable here. So I'm going to let M be the extra men that we want to attend the conference. So now my ratio changes, both the number of men changes, so that becomes 120 plus M, and my total number of people changes because we're adding those men to this group too. So we have 280 plus M there. And we want this ratio, this fraction, to be equal to this 55%, which we do need to write as a decimal. So we get 0.55. And then we're going to solve this. So our lowest common denominator would simply be this denominator of 280 plus M. So we would multiply both sides of our equation by this 280 plus M. And multiplying this side by it, our 280 plus M is reduced to 1, and we're left with basically 1 times 120 plus M, which is 120 plus M. And then over here, we're going to have to take and distribute our 0.55 to our 280 plus M. So our 0.55 times our 280 would become 154, and then that's plus our 0.55M. So now hopefully we all recognize that we have ourselves a little linear equation here, and this is 1M, and since 1 is bigger than the 0.55, I'm going to subtract the 0.55, so my M will be positive. And I want my numbers over here, so I'm going to subtract that 120. So now I have 1 minus my 0.55 would be 0.45 times the M, and this is going to give us 34. And now I'm going to divide both sides by this 0.45. And so I get M is about 70, if I look at this, I'm like 75.555. So what I have to understand here in context is this obviously doesn't make sense for an extra number of men. And dropping it to 75 wouldn't be enough men. So I have to make sure that I round this up. Even if this had been like 0.12 or something like that, I'd still have to round it up to 76 men. And then we write our conclusion. So that's how many more men need to register for this conference so that the percentage of men is 55%. So I'm going to say if 76 more men register for the conference, the percentage of men attending will be 55%. All right, so that concludes our first example. Let's take a look at the second one. So in this problem, we have a save percentage in lacrosse is found by dividing the number of saves by the number of shots faced. So anytime we're doing a division of two quantities, we're creating a fraction or a ratio, and then that's what we're going to look at changing. So our save percentage is the division of the saves by the number of shots that have been faced by that player. So it says a lacrosse goalie saved 9 of 12 shots. And so that's our starting ratio. So we have these saves to the shots faced starts out at 9 to 12. And we're looking at figuring out how many additional consecutive saves the goalie has to make. And the goal is then in that case to raise that save percentage to 0.850. They call it a save percentage, but they're writing it as a decimal. All right, but we could convert that to a percentage if we wanted to, but if it was given as a percentage, we'd have to write it as a decimal anyway. So this is what we've got. So I'm going to define my variable as my additional consecutive saves. And that word consecutive is actually very important because that means that every shot faced after these ones that have already been faced will be a save. If we have any misses in this group, it completely changes the problem. So additional consecutive saves is what we're working with here. So that means that this ratio is going to change by more saves. So we have our 9 saves plus more saves, which is our S. And then our shots faced changes by that same quantity of extra saves, which is our S. And we want this new ratio to be this percentage expressed as a decimal here, this 0.850. And yeah, you could just write 0.85. So then we are going to, again, our lowest common denominator is the only denominator we have, which is 12 plus S. So we're going to multiply both sides by 12 plus S. And over here, the 12 plus S and 12 plus S reduce to 1. So we end up with 9 plus S equals. And we take this 0.85 times 12, and that is going to give us 10.2. And then we have plus our 0.85 or 850 if you want to stick with the full decimal times S. So again, I've got a fairly simple little linear equation here. This is 1S and 1 is bigger than my 0.850. So I'm going to subtract this from both sides so S is a positive coefficient. And then I'm also then going to subtract the 9 to move my numbers to the other side of the equal sign. So I have my 1 minus my 0.85 will be 0.15 times s, and this will be 1.2. Then we're going to divide both sides by our 0.15. And that is going to give us s is, in this case, an exact value of 8. So these are these 8 additional saves. So now I'm going to write that conclusion. So again, I was looking at how many additional consecutive saves the goalie has to make so that his save percentage is this. So the goalie needs to make 8 additional consecutive saves for his save percentage to be 0.850. All right, there we go. All right, and we have a third example. So let's take a look at it now. So the next example requires that we recall some information that we've learned in a previous course, and that is that similar triangles have proportional sides. So similar triangles, remember, have the same shape, but they are different in size most of the time. These will be. So one will be larger than the other, one is smaller than the other, that kind of a thing. And so their sides can't be equal to one another, but it turns out they are proportional. So if you take a ratio of any pair of sides and compare that to the ratio of another pair of sides, those two ratios will reduce to the same number. So that creates a proportion. This ratio equals that ratio in our triangles. And this is an example with numbers to remind you. So if we have these side measures for the larger triangle and these side measures for the smaller triangle, if we take the larger to the smaller with the corresponding, then, and we figure that out from our corresponding statement over here, our similarity statement. So I've got AB corresponds to DE, so that's these two sides. So 10/5, that's this ratio right here. And if I look at AC, it corresponds to DF, so that's these two sides. I have 12/6, and both of those would be a 2. And you can also go triangle to triangle, or in the same triangle if you prefer. So like if I use AB and AC, that's what these are, AB and AC, then I have to use their corresponding sides in the same ratio, which would be this DE over this DF. And so I could do it that way too. Both will work. In this case, both of the fractions equal 5/6. So different values, but still same, they are both equal to one another. All right, so let's apply this concept to this next example. So given our similarity statement, so triangle ABC is similar to triangle XYZ. All right, so here is our example with two similar triangles. So here is our similarity statement, and our job is to find the length of side YZ. And so I'm looking here at writing a proportion of corresponding sides. So the one that I need is YZ, so I keep track of that one. This is the one we're going to find. So once we know what X is, then we'll be able to figure out what this length is. But we got to figure out what X is first. So that's our first goal, figure out what X is. There we go. All right, so now this can be one of those, depending on the problem, some of the setups can give you some really complex denominators. So you need to realize that you have options. For example, you can go AC to BC. You can go BC to AC. You can go BC to what it corresponds to, which is YZ, and then go AC is to what it corresponds to, which is XZ. And just looking at my denominators, I noticed that, not my denominators, but my values here, this trinomial, if I look at its factors, I've got an x plus 6 and an x plus 2, and this has an x plus 6, but they don't correspond. These two guys have a common factor, do not have any common factors. So there are different options here for what we can do. So sometimes when you set it up, you may decide you don't like that setup, and then you can try something else. All right, so a setup that does work nicely is if we look at AC, and AC corresponds to XZ, so I'm going to do that. So that's going to give me the ratio of 4x over x plus 2. Then, because AC came from the larger triangle, I have to go back to the larger triangle for the next numerator, which would be the BC. And then we can see here BC corresponds to YZ. And so that's going to set up our next one. So BC is our trinomial x squared plus 8x plus 12. And then YZ is our x squared plus 6x. Now you might be looking at this thinking that this is really complicated, and it would be, except, as I noticed earlier, the factors of this trinomial are x plus 6 and x plus 2. And if I factor out the GCF of x, it's times x plus 6. So I am allowed to reduce this x plus 6 because they are from the same fraction. So we're going to reduce this, get rid of it, and simplify our problem. So now we have 4x over x plus 2 equals x plus 2 over x. Do not make the mistake of thinking you can cancel those. This is an equal sign. The only way we could have reduced those would be if this was multiplication, and it is not. Same thing goes for those x's there. So now our lowest common denominator is this monomial of x times the binomial of x plus 2. So we are going to now take each of these and multiply by that LCD. So I'm going to take this one times x and x plus 2. And here our x plus 2's would reduce to 1. We're left with x times 4x, which gives us 4x squared. Over here times our LCD of x times x plus 2. The factors of x will reduce to 1. And now we have x plus 2 times x plus 2, which gives us equals x squared plus 4x plus 4. So I'm going to have a quadratic, and I want it in standard form, so I would like my x squared term to be positive. So I'm going to subtract x squared, I'm going to subtract that 4x, I'm going to subtract that 4, and so I'm going to get 3x squared minus 4x minus 4 equals 0. Alright, so now I'm looking to see if I can factor this, and I'm hoping I can. So I've got a 3x and an x, and if I do 2 and 2, I think that will work, because that's going to give me a 6, and a 6 minus a 2, so I want my 6 to be negative, my 2 to be positive, so I get negative 6 plus 2, which is negative 4. Alright, there it is. So 3x plus 2 equals 0. Or x minus 2 equals 0. So this gives me an x of negative 2/3, and this gives me an x of positive 2. So now we're to the point to where we need to use these x's to see what happens in calculating the length of the line segment, or the side of the triangle that we want, which is yz, which is our x squared plus 6x. So don't make the mistake of thinking a negative number wouldn't work. It's always possible that, especially when you have squared quantities, that when you add them together you end up with a positive number. So we do kind of have to check both. It is possible, there are two possible lengths for yz. So we take our x squared plus 6. This is our yz. That's what it was called, yes? Yes. And it is x squared plus 6x. So I'm going to look at the negative 2/3. So if I take the negative 2/3 and square it, and then I add 6 times negative 2/3. So negative 2/3 times negative 2/3 would be positive 4/9. And this, I am going to get negative 4. Well, I can tell that's going to be negative. So because this is negative, I can't have a negative length. So in this case, this one doesn't work. Sometimes the negatives do. And if x is 2, then I have 2 squared plus 6 times 2. And that's 4 plus 12, which is positive 16. And so this is going to be my unit measurement for YZ. So line segment YZ is 16 units in length. And there's our conclusion to finish this type of problem. All right, so that covers all of the examples for the different types of problems on this lesson. So you can go ahead and start the assignment.